All right, this is a video on how to do hypothesis testing when we're dealing with two populations. So just to remind us, a hypothesis test is a way to draw inferences about populations based on samples taken from those populations. Here are the basic components of a hypothesis test when dealing with two independent populations. We say that two sampling distributions are independent if there is no relationship whatsoever between the specific values of the two distributions. And then, like I said, we'll have a chart in just a second that kind of summarizes the different ways. So we state our null and our alternate hypothesis, just like we did when we were doing a single population, except this time you have to have a mu1 and a mu2 or a p1 and a p2. You'll have a level of significance at alpha again. You're going to determine the sampling distribution that we're going to use and calculate that appropriate test statistic. You'll find the p-value using the appropriate table for your test statistic. And then we will conclude with if our p-value is less than or equal to the level of significance alpha, we will reject our null. If the p-value is greater than alpha, we will not reject the null. And then there is the interpretation part. This one's a little different than just a single population. So it says, this includes making a statement about whether the data is significant or not at that level of significance set by the problem. If we reject the null, the data is considered significant at that level. Then we would state either that there is or is not enough evidence to believe that the alternative hypothesis is true at our level of significance. Remember, if you reject your null, you'd be accepting that the alternative hypothesis statement is true. Again, with a margin of error as always, or a possibility of errors. So usually in a two population test, we are trying to determine whether one population mean or proportion, depending on what kind they've given us, is larger, smaller, or different in either way than the other. If we do not reject the null, this relates back to the confidence interval levels that we were looking at when we did chapter 7, where we saw that the lower limits as a negative and having an upper limit as a positive. So when your confidence interval went from negative to positive, remember, we couldn't make a conclusion about that population mean because we could say we don't really know if the mean of one is larger or smaller than the other one because we get positives and negatives in that interval together. So not rejecting the null is kind of related back to those confidence intervals that had both signs on their intervals. Okay. So here's our little flow chart to kind of help us figure out what we have. And I took this straight from the notes, so sorry if it's a little blurry. Let me see if I back out if that helps. Depending on the information available, there's several methods for testing and constructing confidence intervals for the difference of your means or when we do the difference of proportions. In addition, you need to know the original population distributions are both normal, or you have to have at least both sample sizes bigger than or equal to 30. If we know our sigmas for both, we can use the normal distribution. If we know our sample standard deviation instead of our population for both, then we can use the student t. And we will not talk about this scenario in our class, so you don't have to worry about that last one. We talked about that in class. But this is when we know our population standard deviations. So notice we're doing a z-test, and we get, you can also relate back to the confidence interval if you would like. If we're doing a standard deviation is the samples and not the populations, then we use our students t, and we have to have a degree of freedom for that table, and it's the smaller of the two sample sizes minus 1. Okay, and also if you want the confidence interval for that, you can calculate that. If you're doing proportions, it is a little different. So we have two different binomial experiments. We have a number of trials for each, number of successes for each. We have a P1 hat, which is the number of successes out of the number of trials for that first sample. We have a P2 hat, which is the number of successes out of number of trials for the second binomial experiment. We also should have a population proportion for each of those. So what was the historical kind of percentage of success? We'll have our null hypothesis of no difference, which this is how we write our nulls for these difference of two populations. It's the first one minus the second one equals 0, so no change. The alternate will be based on whether or not we're saying is the first one greater than, less than, or just different either way from the second one. And then we have to find this P bar. This P bar is a pooled best estimate for our population probabilities of success and failure. Because we're assuming these are the same, that P bar is our population historical kind of percentage of success. So we add our two R's together and divide by our two sample sizes added together. And then Q bars, just remember 1 minus the population probability of success that we got when we pooled our best estimates. So this is the big thing you have to remember to do. You have to remember to check that each of those is greater than 5 to make sure that you can use the normal approximation for a binomial experiment. So sample 1 times the pooled best estimate of success, sample 1 times the pooled best estimate of failure, sample 2 times that estimate of success for the population, and sample 2 times the estimate of the failure for the population. This is our Z test statistic formula. So notice we do P hat 1 minus the P hat 2 all over, and then these are population estimates. Remember that we calculated up here. It's the P bar times Q bar over this first sample plus the P bar times Q bar over the second sample size. And again, these last 3 steps are the same every single time. Get your p-value using your correct test table. And then if it's less than alpha, we reject the null. If it's not, we do not reject the null. And then we write our conclusion statement. Okay, so that's a lot of information. Let us try some examples. So suppose a researcher is comparing the average scores of students from 2 different teaching methods. The researcher collects 2 independent samples. So there's our mean of sample 1 and our standard deviation of sample 1, and then our number of students in that sample. Then we have our second sample, which has a mean of 72 and a standard deviation for the sample of 9, and the number of students in that one was 25. Suppose that we know that the original distributions are bell-shaped and symmetrical. So since that one sample, that 25, is actually less than 30, it's good that they put this in here, or we would not be able to proceed using our methods and our flow chart that we have up above. So things to note, we have sample standard deviation. So that means we're going to be using the T distribution, the student's T, not the normal distribution with the Z's. And then we would like to know if there's a difference either way in the average scores. Okay, so our null is assuming that mu1, population mean, since this is a sample mean, minus mu2 is just 0. There is no change. We're saying different either way. So we would say instead of it being no change, it's just not equal. It could be less or it could be greater. We're testing a 2-tailed test. Our alpha is 0.05. Determine the distribution to be used and why. So because they told us that our original distributions are normal, which is what bell-shaped and symmetrical means, and we also have sample standard deviation, not sigma, we use the student's T distribution. Okay, so let's get that formula for that test statistic. It is T equals, and then we have our X1 bar minus our X2 bar. Those are our sample means subtracted. There's also the population mean subtracted over here in its own little parentheses we talked about in class. That's for the null, so it's a 0. Then we have our square root of standard deviation 1 squared over sample size 1 plus standard deviation of our sample 2 squared over sample size 2. Okay, so if we plug in everything we have, that would be 75 minus 72 all over. S1 is 8, so 8 squared over 30 plus S2 is 9, so 9 squared over 25 for that sample size. So we'll need to grab our calculator. Let me make sure I'm doing a full screen share. I am. So I'm going to type this in parentheses on top and on bottom, and be very careful. So this is 75 minus 72 on top divided by, open a parentheses, and then I open a second parentheses because I'm going to have that square root in the bottom. If you can do the squaring in your head, fine. If not, you'll use your square button on your calculator. But these are pretty easy ones, I know. So 64 divided by 30 plus, and then I have 81 divided by 25. Close that parentheses and tell it to take a square root of that. Close my denominator parentheses. And I'm getting that that comes out to a test statistic score of 1.294. Okay. I also, because this is student's T, I need my degrees of freedom. So we have to look at both samples. This one was 30, this one was 25, and our smaller one is our degree of freedom. So this would be 24. Okay. So we go to our table for T, and let's erase what we had before on my previous videos. So notice that we're at row 24. So that is this row right here. And my test statistic is between these two guys. 1.294 is in between those. So if we follow that all the way up, and we're doing a two-tailed test, so it is important that you look at the right row because we were doing different either way. That means that, remember, these go descending order. So this would be 20% to 25% is our p-value. So my p-value, if I draw my picture, it's always nice to see it. Because remember, this is a two-tailed test. So we're actually doing 1.294 and negative 1.294. And we're looking at the area in both of those tails. And the p-value tells us the approximate area in those tails. It's somewhere between a shaded percentage of 20% up to 25%. Okay. And since my p-value at its lowest, which would be 0.2 or larger, okay, is greater than my alpha, which was 0.05, we cannot reject the null. Okay, so we write our interpreting statement about that. We would say the data is not significant at the 5% level. There is not enough evidence to conclude that, and then we look back at the way they stated it, there is a difference either way in the average scores on the standardized, or no, they were being taught on different, between the two different teaching methods. Okay, so that whole assumption that it was no change, that null is most likely still true. Okay. All right, let's look at my example 2 on this one. Suppose a researcher is investigating whether a new training program improves performance of employees. The researcher collects 2 independent samples. We have X bar 1, so we're again doing means, not proportions, is 85, sample size of 30. The second sample size was 25 with a sample mean of 75. Suppose that we know the original distributions are normal. Since that one sample is not greater than or equal to 30, that's important to have that statement. From previous studies, we know, so we're actually given a sample, a population standard deviation for both of them. So that's going to be important for being able to use the Z and normal distribution, not the T student distribution. The researcher would like to know if there is an improvement that implies greater in the average performance of the employees. Okay, and we're testing at the 1% level. So the null would be that the difference between the population means is no change, so equal to 0. The alternate, though, is that we're saying there's an improvement in the average employment. So that means that, no, if you look here, this group right here is improved over this group right here, okay? So we would be saying that a mu1 minus mu2 is greater than 0. Our alpha is a 0.01, and this is a right-tailed test. Okay, distribution to be used. Well, they told us the original distributions are normal and sigma is known. So that means we can use the normal distribution. Our formula for our test statistic then would be a Z, and it is the sample mean 1 minus sample mean 2 all over the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Notice not much changes in the formula. It's really the table and noticing that this is a different type of standard deviation. So this would be 85 minus 75 over. We had 12 for the first population standard deviation. That was sample size was 30. And 15 was the population standard deviation of the second group, and that sample size was 25. Excuse me. So on our calculator, we do 85 minus 75 divided by parentheses, parentheses. I can also square those in my head, but you could use your button if you want to on your calculator. 144 divided by 30 plus 225 divided by 25 close that parentheses, take a square root of that group, close my second parentheses, and hit enter. And since we're doing z-score, I can just go to 2 decimal places, so 2.69. So we're going to go and look at a right-tailed test of what's the area beyond 2.69. Let's go to our z table. So 2.6 all the way over to 9 is 0.9964. Now remember, that is the left-tailed area. So we have to do 1 minus that to find the right-tailed area. Remember, always the table of z gives us the area to the left. So 1 minus 0.9964 is actually a p-value of 0.0036 is what I got when I subtracted that. So there's my p-value. And my level of significance was 1%, and that is definitely smaller than 1%. So my p-value and my alpha, if I compare them, I have a less than or equal to, which means we can reject the null. So, interpretive statement. Our data is significant at the 1% level, or the 0.01, if you want to write that. This means there is enough evidence to conclude that the new training program, I'm re-looking at the problem, improved the performance of the employees. Okay, so we're saying kind of population mean 1 is greater than population mean 2, or the subtraction between those is positive. Okay. Now, one other thing to note on this one, because we didn't, all of the ones I've set up for YouTube are kind of p-value situations. Just for a second, let's talk about critical region. Just to remind ourselves about that process. This is just a kind of a little sidebar. Since we were doing the 0.01, if we go to that z table and we look over here at hypothesis testing critical z values, if you're doing a left-tailed or right-tailed test, notice it's 1 for each of them. We were doing right-tailed. The 1% level, that point where you've crossed over and now you're going to reject your null, that happens at a z-score of 2.33. So if you think about that, the place where we're at 0.01 for this area is at 2.33. My score, my test statistic, falls into that region of shading, right? It's 2.69. So if you use the critical region method, you focus on the alpha and you figure out what that z-score would be. Because like I said, I don't usually ask that on a t-table one because it's a little harder. But you would figure out where that alpha is, what's the z-score of that. We have a little table to do that. And then if your test score is in that region, we would reject the null. If it's not in the region, if say it was over here in the part we didn't shade, we would not reject the null. So it's just another way of doing the same kind of conclusion. All right, and then the final example for this set for 2 populations that are independent. We're going to look at this example. So suppose a researcher is investigating whether the proportion of customers satisfied with product A is less than the proportion satisfied with product B. So notice proportions means P, not a mean. So we're not using mu. The researcher collects 2 independent samples. The sample of customers that bought product A contained 150 customers and 90 of them were satisfied with their product. So that's my P1 hat. It was 90 out of 150. That comes out to 0.6 if you divide it. My second sample is that they had product B people, and there were 56 out of 80 of those that were happy with their product. So that's 0.7. And then we're going to need that pooled best estimate for the probability of success, since they don't tell us the probability of success of liking a product. So we take the number of successes in both, divide it by the total number of trials. That comes out to 146 over 230, which is roughly 0.635 if we round to 3 decimal places. So that means my Q bar is 1 minus that, which is 0.365. So I'm going to need all of this information for my hypothesis test. The sample of customers that bought product B, we already read that, sorry. We're using a 5% level of significance. So my null is that there is no change in those that liked either product. The way they've worded it is that A, which is our group 1, is less than B. So that would be that if I subtracted those, if A is less than B, we're going to get a negative. So we're going to be doing a left-tailed test. Alpha is 0.05. What distribution are we going to use? Well, the only time we ever do proportions, we always end up with Z, or the normal distribution, but we have to show something. We need to show that N1 times P bar is greater than or equal to 5. N1 times Q bar is greater than or equal to 5. N2 P bar greater than or equal to 5. N2 Q bar greater than or equal to 5. And just to save time, you can take all of those values and run them through this calculation. They all work, which means we can use the normal distribution as, remember, our approximate for our binomial. The test statistic for this would then be Z equals P1 hat, that's a horrible hat, minus P2 hat, all over the square root of P bar Q bar over sample 1 plus P bar Q bar over sample 2. And that's going to be 0.6 minus 0.7 on top. And then on the bottom, these are a little nasty because I did go to 3 decimal places, but that's kind of the standard, unless they come out nicely. So we have that 0.635 times 0.365 all over my first sample, which was 150, plus the 0.635, 0.365, because remember, that's our estimate for our population of success over the 80. Okay, so this one is a little harder to type into a calculator. Just to also save time, I'm going to give you what I got for this. I got negative 1.50. So if I look that up, remember we're doing a left tail test, so we're only looking for the area to the left of that. So negative 1.5, go to my table, go to the negative part of the Z table. Negative 1.50 is 0.0668. So we're just going to be, unfortunately, too big of a probability to reject the null. Our level of significance was 5%. So since our p-value is greater than our alpha, 0.0668 greater than 0.05, we cannot reject the null. Okay, so my interpretation for this would be the data is not significant at the 0.05 level. This means there is not enough evidence to conclude that the proportion of customers satisfied with the purchase of product A is less than the proportion of customers satisfied with the purchase of product B. All right, and that is the end of this video. So I hope that helps.